Section 4.4 Counting, Key Terms and Concepts, and How to Calculate and Apply Concepts. The multiplication counting rule is a rule used to find the total number of possible outcomes from a sequence of events. Say you wanted to calculate the probability of guessing someone's credit card number by only knowing the last 4 digits. You would use the multiplication counting rule. You would first need to determine how many numbers are in that credit card that are unknown. Say the credit card number consists of 14 numbers. 4 of those numbers are already known, leaving 12 unknown numbers. Next, determine the possible numbers of that card, which would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, which is a total of 10 different number possibilities. You would then solve the equation as 10 times 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 10 for a total of 12 times, which equals 1 trillion. Since this credit card number only belongs to one person, the probability of being able to guess someone's credit card while only knowing the last 4 digits is 1 in 1 trillion. A factorial is used as an exclamation mark symbol, and it represents decreasing positive whole numbers. Like 10 factorial will be equal to 10 times 9 times 8 times 7 times 6. Permutations, the order in which the data is arranged does matter. So if we have 1, 2, 3, we could also have 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. They all consist of the same numbers, but they are different because of how they are ordered. To solve the permutations, you would use this formula on the right. N is the total number of objects. R is the number of objects chosen at once. So, say there is a play audition consisting of 12 participants. 5 at a time are able to come backstage to audition. How many different permutations can we make with this information? So if we use our formula, we would plug in 12 at the top, 12 minus 5 at the bottom. That would give us the 12 factorial over 7 factorial. To simplify that, you would use the factorial 12 times 11 times 10 times 9 times 8 for a total of permutations would equal 95,040. Combinations is the order in which the data is arranged does not matter. So again, we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. They're all the same combination. To solve combinations, you use the formula here on the right. If we look at that same play audition that consists of 12 participants with 5 at a time who are able to come backstage to audition, how many combinations are we able to make with this information? So if we plug in the 12 and 5 in this combination formula, we've got 12 factorial over the 5 factorial with 12 minus 5, which gives us 12 factorial over 5 factorial, 7 factorial. If we break that down, it would be 12 times 11 times 10 times 9 times 8 times 7 factorial over 5 times 4 times 3 times 2 times 1 times 7 factorial. The 7 factorials cancel out, so then we're left with 12 times 11 times 10 times 9 times 8 over 5 times 4 times 3 times 2 times 1, which gives us our 95,040 over 120. To solve that would be 792, so there's a total of 792 combinations.
So let's also discuss how permutations and combinations can be involved with real life examples. For permutations, the first one is going to be pins and passwords. When it comes to pins and passwords, the order matters. So what I have here is if your pin is 0805 for your laptop or your phone and you put 0508, it will still be incorrect because the order matters in how you're putting it in. Another example of a permutation is going to be a phone number. It's a 10-digit permutation, so if you switch around any of the numbers in the phone number, you'll be reaching out to someone completely different. So once again, the order matters in how you're putting in the numbers. For real life examples of combinations, the first one's going to be card games, poker, Uno. So no matter how the cards are dealt to you, you're still given the same hand. So that is why it's a combination, because it doesn't matter what order they're given to you. Another example is going to be a menu. So no matter what order you order something, you'll still be getting the same thing. So the example I have here is a cake. If you order vanilla buttercream with a chocolate cake and pink sprinkles, it didn't matter that you didn't say it in the order the cake's going to be put together. Of course, they're going to do the cake first, then the icing, then the sprinkles. You're telling them what you want, and it's going to be put together in the same way that it's supposed to be. So our first example problem that I have is a researcher needs to select a focus group of 3 people from a pool of 10 volunteers. How many different ways can the researcher form this group? So this is an example of a combination, since the rank of the members doesn't matter, and whether you pick the first or the third person, it'll still be the same outcome. So when you're putting this in your calculator, you would do the 10 first, and then click the PRB and choose the C option, and then you put your 3, and the outcome is 120 for that. For the next example problem I have, it says in a clinical trial with 8 different drug candidates, a lab wants to award gold, silver, and bronze designations for efficacy. How many different ways can these titles be awarded? This problem is a permutation, since we're looking at the rank of something, and the order of the drug being picked in each designation matters. So if it's drug A with golds, drug A with silver would be a different outcome. So it's important which one you choose. So to solve this, you would put in your calculator picking 8, because there's 8 different drug candidates, and then you would click the PRB and click the P option, and then put 3 in. I did 3 because there's gold, silver, bronze, so that's 3 different designations of the awards. And the answer came out to 336 different ways. And the last problem I have is a crate contains 12 light bulbs, but 3 of them are defective. If you randomly select 5 bulbs to test, how many ways can you choose a sample that contains exactly 2 defective bulbs? This is a 2-part combination problem, since the rank and the order doesn't matter how we solve it. But you have to first figure out the defective bulbs. So you would do the 3, C, and then the 2. So 3 of them are defective, and we're looking for exactly 2 defective bulbs, which the answer for that would be 3. Then, since there is 9 good bulbs out of the 12, you're going to do 9C3 because there's 3 defective, which gives you 84. And then we need to multiply both of our outcomes together to give us 252 ways.
Talk about section 4.4 counting when it comes to application of formulas and common challenges and tips. So first, with formulas, we have permutations, which is an arrangement of objects in a specific order, and the sequence does matter. The formula for permutations is equal to n factorial over n minus r factorial. And the formula for permutations with duplicate items is n factorial divided by p factorial, q factorial, r factorial, and so forth. And then the second formula is for combinations, and it is a selection of items from a larger set. And for this, order does not matter. The formula is equal to n factorial divided by r factorial times n minus r factorial. And now for common tips and challenges. One common tip is that you can use your calculator for finding permutations and combinations. You can use calculators such as TI-30, TI-84, or StatCrunch. And another tip is to know when to use each counting method. Remember that for permutations, order does matter, but order does not matter for combinations. One challenge is that different calculators work differently, and so there may be confusion, but you have to get to know your calculator well. Another challenge is that word problems can be confusing. students sometimes struggle figuring out which method to use or what the problem is really asking.